Okay, so let's continue. So the last time we discussed a bit of gravity. So again, I fixed myself that to take the Levi-Civita connection, the usual Riemannian geometry. And then the curvature tensor is defined like here. And what I usually need in GI, I need this contraction of alpha and mu here, which gives me the Ricci tensor. Okay? And yes, indeed, like gravity is in a sense similar to Young-Mills, because we have this kind of antisymmetric derivative of the connection plus the commutator of the two coefficients. If I look at gamma mu or nu, like a left index enumerating the matrices and the two other indices giving me the indices of the matrix, then yes, it's kind of a commutator of the matrices here. So that's the usual definition, and that's basically what makes gravity also kind of like a gauge theory. It would be even more similar to usual gauge theory if I go for tetrads and introduce spin connection for the tetrads instead of the metric, and then it looks even more similar to usual gauge theory, like gauge Lorentz transformations. Concerning the abelian theories, in principle you can also rewrite gravity in kind of more strange terms, like people which are doing what they call periparallel gravity. They describe gravity as zero curvature but torsion, and then it's basically like gauging translations, and then you can have kind of abelian gauge symmetry. So, but I mean, I will not go for just thinking that that's kind of something important. Yes, you can find analogies between different things, but I actually also I would not say that I can derive anything from just idea of U1 gauge invariance, because that's also, it's based upon our usual fields. In principle, when you gauge U1 symmetry, you go for this kind of covariant derivative, and then what you say that at the same time when you rotate the phase of your field, be it scalar field or Dirac fermion or whatever field, at the same time as you rotate the phase, you do this transformation of the gauge potential. But in principle, instead of putting here the vector field, I could put here just some gradient of a scalar field. And then I could say, okay, let's make this translation like chi goes to chi plus theta. And of course, that also would be perfectly gauge invariant, but it won't change anything. And I would not even be able to put any kind of kinetic term for chi without breaking the gauge invariance, because this symmetry means that its value cannot have any objective meaning whatsoever. So, and basically that's how people make covariant teleparallel gravity. They add purely flat, purely gauge spin connection. So, I mean, that's just some comment about these ideas of gauge theories. So I will just go for discussing all these theories without building analogies, except the fact that indeed, the formulas look very similar. So if you learn how to work with one of them, it's my kind of similar. It's easy for you to work with another. And what I also mentioned last time was that the diffeomorphism invariance gives you the idea that the covariant divergence of your equations of motion is zero. Actually, the same is true of your U1 gauge models, for example. This gauge invariance proves for you that the divergence of your equations is zero. But because last time there were some questions about killing vectors related to that, let me tell it again. If you have some tensor field like that, rank 2 tensor field with two lower indices, if I do any kind of coordinate changes, by which I mean I add some kind of arbitrary 4 vector to my coordinates, I change my coordinates like that, then you can find out that how your tensor changes it's what they call Lie derivative along the side of this G. And this Lie derivative is basically a simple thing like psi alpha d alpha g mu nu plus g mu alpha d nu psi alpha plus g beta nu d mu psi beta, something like that. And this guy actually is already a tensor, and I mean that's for any kind of tensor here. But if I take the metric, then what I know also is that this derivative of metric actually can give me the things which mean the connection coefficients, and I can rewrite that simply like that. And here it's not about any killing vectors or whatever. I can take any change of coordinates, and that's how the metric is changed, or any other. Okay, this one is about only the metric. Here that's how about any tensor. Then, if I derive equations of motion, I do the variation of the action, and then the variation of the action gives me variational derivative of my Lagrangian with respect to metric, multiplied by the variation of the metric. Let's assume that I can do any integration by parts I want, so I just derive that. And then I require that this variation is equal to 0 for arbitrary variation of the metric. I mean, the only condition is that, okay, it tends to 0 fast enough to infinity. Otherwise, arbitrary variation, which means that this guy should be equal to 0, and that's my equations of motion. Yeah? But if I assume that my action is gauge invariant, is invariant under diffeomorphisms, that means that if I change the metric not arbitrarily, but only like that, like a Rotary change, it simply cannot change the action at all. Irrespective of whether my field equations are satisfied or whatever, it's just some identical satisfaction here, because that's the gauge invariance. That's the invariance under the change of coordinates. Which means if I substitute instead of variation of G, I substitute this guy here, it must be equal to 0 just identically, with no relation to my equations of motion. Which means if I integrate by parts, that the equations of motion are indeed have 0 covariant divergence, irrespective of whether they are satisfied or not. It's just some identical property. Yeah? And that's indeed true for gravity, because we know that the covariant divergence of Einstein Tensor is 0. But, this proof does not depend on any particular form of the action principle. Even if I go for things like f of r gravity, it shows that again, the equations of motion must satisfy this condition. That if I put the equation of motion instead of G here, still I have identically satisfied zero divergence. So that was some particular point about the meaning of diffeomorphism invariance. And what about killing vectors? Killing vectors are the vectors which show you the symmetry of your space-time. So in principle, if you have this killing vector, you have some symmetry, and like in Newton theorem, you must be able to derive some conservation laws, which follow from equations of motion, not identical things like here. And what is a killing vector? Killing vector, it means that if you make this kind of transformation here, it does not change the metric at all. Which basically means, I can also define it like that the vector is called killing vector if it satisfies this kind of equation. It's not always possible to find the killing vector because not every space-time has the symmetry. And also it's kind of like symmetric 4x4 system of equations. That's 10 equations for a vector. So it's not always possible to solve, of course, except for 0. But if it's possible to solve, then the point is that you do have some kind of conservation law. And that's simple to see actually. Like, if you have the energy momentum, then, okay, let's first start from vectors. If you have it equal to 0 for a vector, then as I told you yesterday, you can find out that with Levi-Civita connection, that's simply like, this thing. And if you have this kind of equation, then it gives you some kind of conservation law. Because you can integrate over some region, and then you get basically the surface integrals, and they can see that, you know, integral of the zero component along some spatial surface changes with time only because of the flow through the boundaries, right? So basically the usual thing like in every other physical theory. But if I have something more here, if I have another index, what can I do? Like, if I add the connection coefficient with respect to the index mu, it gives me basically the same. I get the stuff like this. But I also have one more index here. So I must add also another connection coefficient. Mu goes here. Here, let's say alpha. Yeah. I also have this term. Then, if my tensor was antisymmetric, of course this term is zero for a symmetric connection coefficient at AVG, which means, for example, very analogous to that, it would be also true for covariant divergence of the electromagnetic field strength tensor and things like that. But if T mu is just my energy momentum tensor of matter, it's symmetric. And that means that this term is not zero. And that shows that actually this kind of equation for the matter stress energy tensor does not mean like the usual conservation of things. Yeah? So that's the point. Now, let's suppose you do have some kind of killing vector, which means the vector for which these equations are satisfied. Then let me define another vector. Let's say A mu equal to psi mu T mu mu. Then I can define this kind of vector. And then what I can do, I can find out the covariant divergence of this vector. And let me see. If I act on the A, either I act on the T and that's zero, or I act on the psi, which means I have like this. Yeah? And since my T is symmetric, only symmetric part of this guy matters. But if it's a killing vector, that's zero. So I get some conservation law like in the usual sense. I can derive some kind of integral conservation equation. So that's the difference like for killing vectors. When I derive consequences from the diffeomorphism invariance, it means that my action is not changed by any kind of psi here. That's the diffeomorphism invariance. And from that I can derive this kind of thing for the equations of motion. But if I do have some kind of killing vector, I can do more. I can take the usual pseudo-conservation of energy and momentum, multiply by this vector, and get some kind of conservation. So that's... I mean, for T mu I have just this kind of differential equation, and that's not a real conservation, yeah? Because I cannot produce like, some integral thing. But if I have some symmetry, it means I have some killing vector. And then either from Newton's theorem or multiplying like that, you can derive some like real conservation of something. And depends on what you have. Like, if it's some kind of time-like vector, it's something you might call energy and what. So, okay, that's the point for this equation of the last time. Okay, and now let me switch to cosmology. Now the main topic would be cosmological things, and to be kind of simple, I want to fix the spatially flat cosmology, just to not have troubles with spatial curvature. And let me first start from this kind of metric. Yeah. So it's just some spatially flat cosmology with some scale factor here. Okay? So, in principle, yes, you know that you can substitute the metric to some computer program, and that will derive for you everything. What I want now to show, like in some 10 minutes, is that you can do it by hand because actually the calculations are not so deep. I mean, if you look at the formulas, basically, what's the problem here? It's just that you have many summations, and everything should be done accurately. You have also inverse metric here, so that's kind of difficult. But otherwise, everything is very simple. And when you have some very symmetric space-time, you can do calculations by hand. Like, for example, this metric, it means that G00 is equal to 1, and Gij is equal to minus a squared delta ij, and G0y is equal to 0, right? That's just the components of my metric here. And for this diagonal matrix, of course, it's very simple to find the inverse matrix. Doesn't require much. So G00 is again 1, G0I is again 0, Gij, I go to find the inverse matrix, that's minus 1 over a squared delta ij. That's it, right? So then we want to calculate the connection coefficients, and from the connection coefficients you can immediately get a Ricci tensor, and that's what we need. If we look here at the connection coefficients, you know, the metric is diagonal, which means that also the inverse metric is diagonal, of course, which means that only alpha equal to beta means something. So basically I have these derivatives here. Derivatives with some index in derivative and two other indices in a metric. Since you know all the dependence is only on time, it means that one index must be 0, so that I have time derivative, and other two indices must coincide because my metric is diagonal. And moreover, they should be spatial because G00 does not depend even on time. So basically, which means that means that the only things I can have are like that. Okay, and I should be equal to J. Or like this. Right? Nothing more can I have from here. All other possibilities would give me 0. Just obvious. Right? And so if I go like for this one, it means that I have to take time derivative like here, alpha is equal to 0, so which means that I will have minus time derivative here, and minus time derivative of what? Of the spatial components of the metric, so minus and minus give me plus, and I have like 1/2 over 1, and then multiplied by derivative of a squared, which basically means that I have a squared. That's it. This guy can also look here. Okay, one of those indices is equal to 0, so one of these first terms plays a role. Here is just some spatial thing, which means I have to take this inverse metric here, and then I take time derivative of again like this metric here, and basically which means here I must put delta ij. Here I must put a dot over a, again delta ij. And after that I have to have a look at this R menu and substitute what I found there. And let's do, for example, just one of the components, and then I will leave it for your exercise. Like R00, for example. I look here, okay, I have here I should like gamma 0, 0, which means I don't have that. I don't have any gamma with zeros. So, okay, the first one is 0. Then I go more, and here I get like time derivative minus time derivative of what? Of some trace here. Trace of gamma alpha alpha 0. Okay, it is 3 times this thing. So it goes like 3 times a dot over a. Then I go more. Again, here I have gamma 0, 0. There is nothing like that. It can only be 0. And then finally I go to here. And here is 0, here is 0, and I have, summation over all possible things like here. And again, what can it be? It can be just these things 3 times, because for all possible values of I and j. So then finally I get like minus 3 times a dot over a squared. And so here, if I take the derivative with respect to the denominator, it cancels this guy here. And if I take the derivative with respect to numerator, I get minus 3 a double dot over 8. And that's it. Then you can try to find R0I, and then you can have a look here, like 0I you put here, then you must have time derivative here, and then you need 2 zeros. There is nothing like that, 0. Then here you have derivative with respect to I, nothing depends on special components, again 0. Here you again have like 0I, which means that you must have some spatial row. Then spatial row goes here, and then alpha either it's 0, then you have 2 zeros, or alpha is spatial, and you have 3 spatial components, nothing like that you have, 0 again, and here also you see 0. So basically you very easily see that R0I is 0. And then analogous we can find the spatial components of R, and that's how it is. So it's very simple to do. There is nothing you need computer for. You can spend 10 minutes in this.
To go through the R0I, because we know that G mu nu is diagonal, and we know that T mu nu is diagonal, so R mu nu must be diagonal.
Yes.
Just diagonal.
Right. I mean, the metric is diagonal, yes, but if it depended like on many different coordinates, the Ricci tensor might have been non-diagonal.
So like we need something diagonal to add to something diagonal to give us diagonal from the Einstein equation, right?
Yes.
So it
But-
must be diagonal. It's the same equation.
I mean, if you here why it's diagonal is also because my diagonal components depend only on one coordinate here, on t. If it depended like on all 3 coordinates, if you try to calculate all these things, you would find also non-diagonal terms. Yes, that's because of isometry. If I did have something non-zero here, it would mean some kind of preferred direction. So yes, you can also try this kind of idea, but even if you are kind of not sure about symmetry considerations, you can just honestly calculate the things and see that it's 0. And that's not so difficult, okay? So that's something I want to show, that in principle these calculations are not so difficult, okay? Then, okay, let me then not spend time more. And I can just give you the final answer. The final, okay, and on top of that, let me say that they define what is called Hubble Constant, which is a logarithmic derivative of the scale factor, okay? And of course, you can also then calculate the time derivative of h, and that would be something like that, and more, okay? And then the equations you get, like the 0, 0 component of Einstein equations will give you the Hubble constant squared related to the energy density, and something which also depends on the time derivative of h related to the pressure. Okay. So that's the Friedmann equations for spatially flat cosmology. In principle, yes, if you wouldn't reduce also spatial curvature here, you could also do the calculations, but it would require a bit more effort. And now, what I'm going to discuss is that in principle here, I chose some kind of natural coordinates, of course, because like if geometry of your space-time is like you have some flat planes which just change with time, and you have your time thing, So that basically you have like at every fixed point of time, you have Euclidean geometry here, and the scales of this Euclidean geometry, they change in time. Yeah, they're like an expanding universe. But that's not the only possible choice of time, right? Because in principle, I can go and change the time like some nonlinear function of time. And that won't change this thing, but what it will change is that here, I might have like arbitrary function, usually called lapse. Arbitrary function of time in front of dt squared. So that will be just different choice of time. The choice of time which also respects all the symmetry I have here. So somehow I have the freedom of choosing time variable. Just from the point of view of symmetries available in the space-time. And actually you can play the game. You can try to change the time, and you know that the Einstein tensor is a tensor. So you can understand that if you change the time variable, the components of the Einstein tensor, they change like a tensor, of course. And I mean, in principle, you can also go the same way. Like here, you can calculate the Ricci scalar. The only difference would be that because now also G0 is not 0, then you will have non-zero gamma 0, 0, 0 component. Otherwise, the calculation will go the same way, basically. And why it's important for me now is because now I'm going to start discussing cosmological perturbations. Like, okay, I have this kind of cosmology. That's some kind of very simple, very symmetric space-time. And that's why I am able to solve equations. Otherwise, the equations would be very complicated. And now I want to add some perturbations around. So on average, I have this kind of spatially flat space-time. And I want to study what happens if, you know, the space-time has some perturbations around this solution. And very often it's, I mean, what I had here, like dt squared, is called physical time. But, you know, if I have physical time, then, you know, the spatial and temporal components are kind of different. These ones have a squared, time has 1 in front of it. So, very often for cosmological perturbations, it's much more convenient to go for what I call conformal time. And conformal time means that I find the time coordinate in such a way that I have the scale factor just as some factor in front of Minkowski metric. How can I do that? Okay, if I had physical time, I have to find such a change of variables that dt is just a of tau d tau. And if I do this kind of change of variables, then from dt squared I get a squared d tau squared. Just some simple change of variables. And after that I have my metric in this form, and that's what is called conformally flat, just because, you know, except the overall factor, like conformal transformation, you have just a flat metric, just the usual Minkowski space-time. Nothing more. And then, on top of that, now we can try to find the perturbations. Okay? So now the idea is that I assume that I have space-time geometry very similar to this metric, and I want to find what happens if I change geometry a little bit. And of course, if I study Einstein equations, I also have to study what happens on the right-hand side if I change that a little bit. So, I mean, usually like
that's obvious, but maybe it's just to make it explicit that you are perturbing away from homogeneity.
Yes.
From the idealized homogeneous space, he's perturbing away from putting different perturbations.
Yes. So of course, yes, here the space is homogeneous and isotropic, like in spatial sections. In time, not precisely, because in time I can understand dependence here. And now, yes, I want to go like beyond that. I want to go to inhomogeneous perturbations. Also, the same is true for the right-hand side here. I have some homogeneous energy density and pressure. I want to go for some perturbations around these homogeneous values, right? anyway, in many cases, what is enough for me in cosmology would be the energy momentum tensor of a perfect fluid. That's the energy momentum tensor of this shape. Rho is the energy density, P is the pressure, U mu is the four vector velocity, which by definition has unit norm, and G is the metric. Yeah. Then what would I have here? I would have here like T00, okay, and the background value is that A0 is equal to, okay, let me say, the background value is that the spatial components of the velocity are 0. Yeah, that's my background value. The four vector velocity just goes along time, right? And that means that A0 multiplied A0 lower index is equal to 1. And because now I have not 1 here, but A squared, I can say that, okay, let's say my A0 is like 1 over A, and the 0 lower is A. Then multiplication gives me 1, and if I erase the index by my metric, then yes, A with lower index goes to A with upper index. So somehow, because I have this kind of overall factor in front of Minkowski, like a real physical thing is kind of geometric average between upper index and lower index. And now I want to do some perturbations. And like I'm going to study only linear order perturbations. So at linear order, I get the AUI non-zero. And I also usually prefer to study mixed position of indices, one up, one down, which means I have this and that's kind of very simple then. Any kind of metric gives me just a delta function here if I take one index up, one index down. And now, if I go for T00, I have like U0, U0, and since it's different from 1 by square of Ui, then U0, U0 still gives me 1 at the linear level. And I basically have rho plus P minus P. P cancels itself, and then I will have like T00 gives me rho plus delta rho. That's the first order perturbation of the energy density here. Then if I go to here, T0I. Okay, 0I means that I have here Ui, and that's already first order perturbation. So all the rest I take like the background level. U0 with upper sign is like 1 over A. So what I get like 1 over A rho plus P Ui. Rho plus P at the background level, no perturbation. And Ui is the first order perturbation of the otherwise zero spatial velocity. And finally, if I go for spatial components, then the first term is just 0 in linear order, because I have Ui, Uj, they are both first order perturbations. So at the first order, in the spatial components of the mixed indices, only the last term matters. And that gives me like Tij equal to minus P plus delta P delta Ij. Yep, that's the perturbations of the energy momentum tensor, which I will have to put to the right hand side of the Einstein equations. Yep, that's the whole story here. And what we usually do in cosmological perturbations, we take this vector, velocity vector here, and I decompose that into the divergenceless part and the gradient part. by definition, I assume that the divergence of the u tilde is equal to 0. So basically, if you remember something about hydrodynamics, that's basically like I divide like the motion to potential flow and circular motion. Yeah? Why is that? Is because if I have some equation, some vector equation, and then I have some divergences part and some gradient part, I can take divergence of this equation of motion, and the vector part goes away, and for the scalar part I get Laplacian of u equal to 0. And if I go for perturbation theory, this kind of things like Laplacian of something, I solve like this something is equal to 0. Because otherwise I will either have some growing thing, or I will have like 1 over r solutions for 0 Laplacian. That's not something I consider as perturbation. So I assume that it should be just some kind of simple wave solutions on top of the homogeneous equation. And so that's why, when I consider perturbations around the spatially isotropic and homogeneous space-time, I would equate to 0 separately, divergences parts and gradient parts. So that's the basic idea here. Or for particle physics people, you can also say that I go for irreducible representations of the rotation, spatial rotation. If I did have some kind of preferred direction here, then of course it won't be true. But if I had preferred direction, I could have some kind of contraction of my velocity with some preferred vector, and then I would not be able to separate like circular motion and potential flow. So that's the point here. Okay, and now okay, what I forgot to tell you that once I change the time variable, of course I also have to change on that side of Einstein inflations, because I work on different elements.
If there is a direction, we can even also postulate on the preferred direction of the different, right?
Yes, that we can do.
So this could work, but with respect to this preferred direction.
Yes, but here the point is that I don't have any preferred direction, and so that's why basically these two things they just don't interact with each other. So that's the idea. I mean, you can study like cosmologies like BNP1, which have some kind of preferred direction, but then the cosmological perturbation theory looks more difficult because you cannot just separate the gradient and the divergences parts into separate equations. They kind of interact with each other. Yeah, just because if I have the only directions are perturbations, then at the first order, linear order, I cannot put them interact with each other. They go like separately. Divergences part and gradient part. Yeah. And if some vector is equal to 0, it must be like for both separately for divergences part and for gradient part, because 0 Laplacian would be just something which is not a perturbation. Okay. But if you have preferred direction, you can go in like you would have some scalar plus some vector, and the vector multiplied by some background vector, and still that's first order. Right? So if you go for some preferred directions, you cannot separate scalars from vectors. They do have some interaction via the background directions. So the point is that yes, if I'm studying just linear perturbations around absolutely isotropic and homogeneous space-time, I can study separately scalars and vectors. Or let's say divergences vectors and gradients. In other ways, like this kind of guy is like some longitudinal perturbation, and this one is transverse. If you don't have any kind of preferred direction, yes, the longitudinal things and transverse things should be equal to 0 separately. If you do have preferred directions, then yes, you lose this kind of good thing. Yeah, so that's the point. Okay, so that's what I need for perturbations of the energy momentum tensor. I will just leave the perturbations of the energy momentum tensor down here, and on top, let me first say about the background solutions, because yes, what I forgot to mention is that of course even background solutions are kind of not solutions, but the shape of the equations they change because of the different choice of time variable. And here I had it like that, and here I can introduce like curly h, which let's say a prime over a, and by prime I denote the derivative with respect to this tau. And since the physical time dt is related to that like a t tau, it means that if I have this kind, if I take this kind of derivative, that would be like a times larger than h in terms of the physical time. Yeah. So if just h is a dot over h, and a dot means like I had dt squared minus a squared, anything else, then if I go from this time variable to this kind of time variable, it means that the derivative, that the differentials of t and tau are different from each other like here. So basically, time derivatives with respect to this tau thing are like a times larger than time derivatives with respect to t. Just change of variables of my derivatives. And then basically all the things getting multiplied by a squared, and then finally I find out that in this new variables 3h squared will be like 8pg a squared rho, similar to here. But you know, since I would change the time variables, the time components of the Einstein tensor got multiplied by a squared, like here, and so the right hand side also gets this a squared here. And another equation would be like 2h prime plus h squared equal minus 8pg a squared. Yeah, like that would be the spatial component of the Einstein equations. And actually what I want to say is that actually here, this is the same as I have here. Why? Because this h curly is like the usual h multiplied by a, and that's why if I take another derivative of this h, I get again like h dot, like at worst, but plus also another h, like h squared. And that's 2 times here. That's why plus 1h squared here is the same as plus 3h squared here. So you just have a change of variables in my equations. But otherwise equations are the same. So that's you have to bear in mind. You know? Your equations are dependent on what kind of coordinates you have chosen. And if you compare your calculations with some other calculations, you have to be sure that your coordinates are the same, or you have to change from one coordinate to other ones. In principle, it's not so difficult because it's a tensor. Your Einstein tensor is a tensor. You know how they change under coordinate changes, but still requires some, you know, attention. Okay. And then let me talk how to do the perturbations. Like, you know, in the right hand side, I wrote it here, very simple. In the left hand side, you have to find perturbations of the Einstein tensor when you perturb your metric a little bit. Okay? And so, I mean, if I would try to do that accurately the whole way, it would take like several lectures to just calculate the things from the platform. Just because, you know, you have many components here and you have to calculate all the summations over all the repeated indices, and it takes time. So my idea now is that I explain like the basic ideas of how you should go, and then I will just write down the final results. So let's assume that I have, to start with, let's assume that I have a metric which is Minkowski metric plus some small perturbation. Of course, for Minkowski metric, like in the usual Cartesian coordinates, I get 0 gamma and 0 curvature. Yeah? So what happens if I add some small correction to the metric? And let's say I'm going only for linear order. When I look here at the connection coefficients, okay, this guy is just Minkowski. These guys, they were Minkowski, but they had derivatives. Minkowski has constant components, so that's why you had 0 here. Yeah? Derivatives acting on the constant components were giving you 0. Now, we change eta by some small correction. You can either change here or here. But if you change it here, it doesn't give you anything because here at the background level you still have 0. So the only non-zero result at the linear level around Minkowski would be if you add h to these terms here. And here you just leave Minkowski. Because changing also here would also take you to the second order. Okay? So then basically it means that gamma alpha mu nu at the linear order you will get like 1/2 eta alpha beta, and here you take like d mu h beta nu, d mu h beta mu minus d beta h mu. Okay? So that's the only way you get non-zero at the linear order. You add perturbations to these terms with derivatives, and you leave the prefactor Minkowski. And then you substitute that to the Ricci tensor, and your Ricci tensor, okay, your background connection coefficients are 0. So these terms are quadratic in the perturbations. Just forget them at the linear order. So the only thing which happens, you change here. So at the linearized level, you get the Einstein, the Riemann tensor like that, like d mu gamma alpha mu beta minus d mu gamma alpha mu beta, and that's it. Here it's like plus O of h squared. Here the same. At the linear level, that's all you get, right? And basically that means that here, okay, here you have like 3 terms with derivatives of h. You substitute here, you get like 6 terms with derivatives of h, linear terms in that. You make a contraction, you find the Ricci tensor, you can find the Ricci scalar, and then you can construct the Einstein tensor. Einstein tensor, I remind you, is just r mu minus 1/2 r g mu. Moreover, here instead of g mu you put just Minkowski because already r is only first order correction. Yeah? So basically here you get eta mu nu multiplied by something from Ricci scale. And if you just accurately substitute that one into another, you get a result. And that's you get the result which Maria Jose showed yesterday for this linearized g mu nu around Minkowski. So that's how you can get it. Very simple. What happens if your background metric is not Minkowski? Then, of course, if it's not Minkowski, then you have more troubles here. First of all, yes, if it's not Minkowski, then also you have some non-zero derivatives here, most probably, right? So that means that you also have background contributions to these derivatives, and that means that you have to go for the first perturbation to the metric here. That's kind of not so difficult, yeah? It goes like that. You just find like inverse matrix to the first order, and that's just subtracting this h. So that's simple. But then yes, on top of these terms, you also get more terms with derivatives of background g multiplied by perturbations of g here. Yeah? So I'm not going to show how it works, but just to give you the final result is that basically the first order variation of gamma, the gamma was not 0, of course, now, if you take g here instead of eta. The first order variation you can find very simple, like you put here g alpha beta, and here instead of the partial derivatives, you put the covariant derivatives with respect to the unperturbed metric. So you did have some covariant derivatives in the background solution, and you just use them here. That's your first order variation of gamma. And then here you also find the variation of Ricci tensor, and again it's not just the whole tensor, just variation, because you probably did have something non-zero. And basically you can show that the first order variation basically gives you just the covariant derivatives of the variations of gamma. So that's how you can do the same the thing. I mean, it looks very simple, but actually it's not so simple if you really try to calculate precisely what you get there. And the one point which I have to make here is that sometimes you can find some simplifications because your geometry is not so difficult. And in particular here, the simplification I have is that my geometry is almost flat. It's just multiplied by some a squared of tau, some conformal factor. And in principle, I can try to define the perturbations like inside this flat metric. Not like Okay, let me write it. I can define the perturbations like the following. Let's say I have g nu nu is equal to a squared of tau or t. Let me now forget about different time variables. I will also use this conformal. And here I put like eta nu nu plus some perturbation. Okay? That's my right to parameterize my perturbations the way I want. I could add h mu just to know separately, but I can also add that like in these brackets. So that basically I have perturbations of the Minkowski metric, and that is multiplied by common factor a squared here. Okay? So that's the way to study perturbations. And what I can also tell you is that in principle now, if you have your metric multiplied by some conformal factor, you can actually find how it changes your geometric moments. So let's assume I have metric g mu nu, and they change that by multiplied by some factor. Okay? And then if I denote that, like, let's say I define omega, which is the logarithm of a, and you can substitute that here. What happens? If your a squared is just constant, it doesn't change anything, yeah? Because you have a squared here, and you have 1 over a squared here. So constant rescaling of the metric does not change your geometry at all. And then, but if your a squared depends on something, like here it depends on time, I also get some more derivatives here. Okay? So basically I get derivatives of omega. Precisely because I substitute the logarithm, and then the derivative of logarithm gives me just derivatives of omega. So finally I can substitute it here, find out what I get, and I can see that the Ricci tensor, okay, let's say that this metric I call it g mu nu tilde multiplied by a squared. And the final result, if I do the calculation, if I substitute it there, would be r mu nu tilde is equal to r mu nu minus second derivative of omega. You know, the first one is just the usual derivative, just a scalar. But the second derivative should be the covariant derivative. Covariant derivative with respect to the initial metric, this metric. So I have to take care of the first corrections to the partial derivatives. Then minus g mu nu elongation of omega plus 2 times d mu omega minus 2 g mu d omega squared. So you can do these calculations, not so difficult, but it requires some time, and you can find this thing. Then in principle, that means that if you have found perturbations around Minkowski, you can transform the perturbations around this metric, like, you know, by just applying this transformation. It's like not precisely absolute elementary. I mean, these parts are kind of simple, of course. That's just the usual derivatives. But here, with second derivatives, we will have to take care of the first corrections to the Minkowski case, which is partial derivatives. Okay? But otherwise, yes, finally you can find out what you get here. And so the question now is, what do I get from this approach? And for the last like 5 minutes, I want just to write down the result. And then we can discuss next time. We can discuss what it means. So basically, let me say the following. Okay, I want to find perturbations of the metric like this. I want to find perturbations like Minkowski plus some correction, and only after that I multiply by a squared. So that's my way of finding perturbations. And then I want now to parameterize perturbations of the metric. Yeah. I will do it the following way. Like G0, 0 will go like a squared 1 plus 2 phi. So yes, I just denote the deviation from 1 by some kind of field phi. Number 2 here is just some convention to be like, close to the usual Newtonian potentials in gravity. So in principle, this is not necessary here, just some convention which is very nice to have. And then the spatial mixed space-time components. Here I don't have background, yes, so the background level of the mixed components are 0. But in principle here I have like some spatial vector, and as I told, I want to separate divergences vectors and gradients. So I say, okay, here it would be like this. And by definition I assume that the vector V is divergences. Okay? And finally in the spatial part, again I put a squared, and here yes I did have background value minus 1 minus, let's say, 2 psi, that's another Newtonian potential, delta ij, that's diagonal part here, plus 2 times the second derivative of another scalar, plus symmetrized derivative of a divergences vector, plus the piece which should be transverse traces. And by transverse traces, I assume that the trace of this guy is 0, as well as any divergence is also 0. Okay? So that's the way I parameterize any perturbations of the metric. So I have here like phi, f, psi, s for scalars. I have 2 divergences vectors, v and c. That's like 4 more components, because each 3-dimensional vector which is divergences has 2 independent components. So 4 components here in f, phi, psi, s, 4 components in v and c, and I have this guy here, which is symmetric 3x3 matrix, so it's kind of, in principle, it must have 6 components, right? And I subtract 1 restriction at its traces, and 3 restrictions and all 3 divergences are 0. So I subtract 4 conditions, it has only 2 independent components. So 4 components in scalars, 4 components in vectors, and 2 components here, 10 components, which is like 10 components of the symmetric matrix of the metric, right? So, and basically this guy is what is called gravitational waves. That's the only dynamic comparison. And the final point I want to make now is that here I still did not fix gauge freedom. And the gauge freedom means that I can change the coordinates like this, right? How do I change the coordinates? I have another guy here, and I also want to classify that with respect to the SO3 rotations. I basically have a time component, which for spatial rotations is just a scalar. And I have also the spatial components, which I can again decompose, like some gradient of some scalar plus some divergences vector. Okay? So with respect to the rotations, spatial rotations, I have 2 scalars, time component and the longitudinal component of the spatial thing, and I have 1 spatial vector, like 2 independent things here. So, and I can play with those guys. I have like 2 scalars to play with, and I have 1 divergences vector to play with either. Which means that if I want to choose the gauge, out of 4 scalars here, phi, f, psi, s, I can choose 2 of them and kill another 2. For example, the usual Newtonian gauges, I kill f and s and have only phi and psi. And again, out of vectors, I have 2 vectors here, v and c, and I can kill 1 combination of them, and still have only 1 divergence vector for perturbations. And since I have no tensors here, this guy is gauge invariant. this gauge is gravitational wave, which is gauge invariant. So tomorrow I will just start from this representation. I will choose a gauge. The gauge will be that I will kill F and S, leaving only phi psi. And in vectors I will kill C, leaving only V. And after that I will just show what kind of equations you get if you substitute this this variation of gates, if you substitute here and then calculate the Einstein tensor. So then you will see what you get out of that. And then you equate that to the right-hand side of the Einstein equations, and that gives you the full system of linear cosmological perturbations for your cosmology. So that's how it works. I hope it was kind of more or less clear how you can do the calculations. Even though, yes, I cannot show precisely how to do that, because I will have like a couple of lectures to just do the calculations here. Because I mean, it's very simple. There is nothing like deep, difficult, or whatever. It's just that you have many terms and they have to be accurate. Nothing more. Okay, so then I think, yeah, that's it for now. Any questions? Yeah.
What are these equations?
I mean, you know, when you write this kind of cosmology, it's just some homogeneous and isotropic universe which has nothing inside. Yeah, it has some uniform matter which changes its energy density and pressure, and just a boring solution with no dynamics inside, just some global time dependence. But our real universe is not like that, right? We have our sun, we have some galaxies around, and also initially, like in the early universe, it was not fully isotropic and homogeneous. It did have some, perturbations there. So what we want to describe how these perturbations evolve according to the laws of general relativity, to the Einstein equations. And then, once we can do that, we can also compare with what we see like in the CMB, in cosmic microwave. So that's the idea. We want to apply Einstein's theory to small perturbations around that. And those small perturbations there can be seen both in CMB and like in the meta distribution in the universe, like large construction. So once we do that, we can compare our theory and observations and then see how well we are doing. So yeah, that's the principle.
So when we plug the Einstein's here in Einstein's equations, we get the dynamics of the units.
Yes, yes. So you get the Einstein tensor, you get perturbations also the energy momentum tensor of your matter on the right hand side, and then you try to solve and see how it must evolve. And if your predictions coincide with your observations. So that's the point. Okay. Okay, then a small break, and after that we continue with numerical relativity.